Hello everyone, welcome to my talk. Today I'm going to talk about low overhead and context-sensitive profiling of GPU-accelerated applications. My name is Keren Zhou. This work was done when I was a graduate student at Rice University with Jonathon Anderson, Xiaozhu Meng, and John Mellor-Crummey. So in the field of HPC, we care about GPU-accelerated applications because top supercomputers are accelerated by GPUs. So here's a table that shows the top 10 supercomputers from the top 500 list published this year. We can see that 7 out of 10 supercomputers are accelerated by GPUs. However, previous study has shown that GPUs are not utilized well in important workloads. So this chart shows the GPU utilization rate for 19 important deep learning neural networks running on a single NVIDIA GPU. We can see that the average utilization rate among all the workload is only 56%. And there are about half of the workload that only uses the GPU less than 50%. So before diving into specific analysis for GPU accelerated applications, I'd like to give you a sketch of how GPU execution is scheduled using CPU. So unlike CPU programs, GPU programs are not directly scheduled by the CPUs. Instead, the CPU has to issue some commands to the GPU to let it offload work from the CPU to the GPU. Let's get started with a mem copy command. After issuing this command to the GPU will receive a task to copy memory from the CPU to the GPU. Next, suppose we are going to issue another kernel launch command. Then the GPU will receive this command and start a customized GPU kernel to perform some computation. Note that the CPU and the GPU are running asynchronously, which means that after CPU issues the kernel launch command, it can do whatever it likes to perform some computation on the CPU side. Then once it needs the data from the GPU, when the GPU kernel is done, it needs to send another memcopy command to the GPU to let it copy the data from the GPU to the CPU. To guarantee that the data is ready, the CPU has to issue a synchronization command to synchronize between the CPU and the GPU. So GPU performance tools analyze GPU operations running on a GPU and derive important metrics. There could be several measurement modalities for GPU performance tools. For example, we can intercept core scoring GPU operations to get some core scoring metrics, such as the time for each operation and the number of threads used by each GPU operation. Besides, we can also instrument instructions in GPU kernels to inspect detailed behavior of each GPU instruction. Otherwise, we can also use hardware counters, such as instruction sampling hardware counters in GPUs, to sample instruction behaviors. So nowadays, there are many performance tools available provided by vendors, including NVIDIA's Nsight Systems, Nsight Compute, AMD's Rock Profiler, Rock Tracer, and Intel's BTune. These tools can output performance metrics for both core scoring metrics and fine-grained metrics for users. So here is an example output provided by Nsight Compute. We see this is a flat profile because it only provides us metrics associated with each GPU API. For example, at the top line, I outlined metrics associated with the CUDA memcopy operation, which shows the number of calls, the total duration, and the average duration. However, we don't know where this CUDA copy is called from in our program. A program could have thousands of places that calls this CUDA memcopy, but it's not shown in this flat profile. This problem is widely existed in modern GPU programming models because they generate sophisticated CPU calling contexts. For example, I mentioned that a GPU API can be invoked at different places. Besides, modern programming models such as TensorFlow, PyTorch, Cocos, and Raja also generate complicated code with many small procedures on the GPU side. So we'd also like to have sophisticated GPU calling contexts to guide us perform optimization. So to this end, we build our tool that output a context-sensitive profile field. In this field, on the left part, you can see that their calling context span from the CPU to the GPU, leading to a hotspot on the GPU. Besides, on the right side, we associate GPU instruction counts or GPU instruction samples for each frame that is shown in the left side. So essentially, we can clearly see the hotspot on this GPU kernel and know where this hotspot is incurred in the execution based on the calling context. To build such a tool, we need comprehensive measurement and analysis. So in this slide, I'm going to show 3 important components included in our tool. The first part is that our tool intercepts GPU APIs, and at each interception point, we are going to unwind the call path associated with the GPU API and insert the call path into a calling context string maintained at runtime. At each GPU API, we're going to generate a unique correlation ID. Then we're going to send through pairs of correlation ID and call path to the measurement runtime. Next, we are going to offload the GPU operation to the GPU for execution. After the execution is done, the monitoring runtime, like NVIDIA's CAPTI, will return pairs of correlation ID and metrics to the measurement runtime so that we can essentially correlate call path with metrics and generate pairs of call path and metrics. Then the measurement runtime can attribute metrics to call path in the calling context tree. Next, offline, we're going to generate GPU device context. Like I just mentioned, we have incurred many challenges in building our tool. First, to unwind the call path, it appears that many sophisticated GPU accelerated applications could have very frequent GPU operations and deep call path, which causes high overhead to our tool and runtime. Besides, for applications with large number of GPU operations, they often incur massive measurement data, which in another way also incurs high overhead to our tool. Besides, on the GPU side, we found that there's no vendor-provided API for us to unwind the call path on the GPU. Therefore, we have to derive our own method to get the GPU device context. In the next sections, I'm going to provide solutions for each of the challenge. Let's get started with the memoization-based unwinding method to reduce the call path unwinding overhead. Before diving into the details, I'd like to show you a little bit background about how we measure and attribute costs in context. So at each GPU API, we will first unwind the call path. The unwind procedure is done by reading the stack of the current PC, which walks all the way from the current PC to the main entry point, where you could have a series of call instructions. Next, this call path is fetched and inserted into a calling context tree maintained by the runtime or the tool. So obviously, the overhead or the problem incurred by this procedure is that walking the call stack, especially when the stack is deep, will incur expensive cost. So to get you more sense for this problem, we provide statistics for applications we studied in this table. For each application, we'll provide the number of GPU operations per second, the unique call path associated with this application, and the average call path depth. So from the first column, we can see that each of the application actually incurs high frequent GPU operations. So we can see that for applications such as Lagos, it has more than 200,000 GPU operations per second, which is quite a large number because for CPU sampling, we could have only 2,000 samples per second. Besides, what's more important, for each GPU operation, their call path is also very deep. So based on these two problems, we can see that how we could incur high overhead for our tool. However, we also found one unique property for these GPU accelerated applications. We found that among all the applications, their unique call path could be relatively small comparing to the number of GPU operations, which means that we can probably derive some identifiers for unique call path and map this unique identifier to the call path so that we can just get the call path by compute identifier instead of working the whole stack. So our idea is to use easy to compute identifiers to represent call paths. Next, I'm going to show you this specific example to demonstrate how we derive a complete identifier mechanism to get accurate call path. So in this sample program, the main function will call function A. In function A, it's going to launch a GPU kernel K, following by a for loop where each iteration is going to call function B. Function B calls GPU kernel K, following by another for loop where in each iteration it calls function C. In function C, it's going to launch kernel K, G, and kernel G at two different places based on conditions. So at first, we get the call stack of call path for K1 and call path for K2. So we can observe that their stack heads are actually different. Therefore, the very primitive identifier that is easy to compute can be read through the stack pointer register. Since K1 and K2's stack head are different, the values in their stack pointers will be different. However, this simple mechanism doesn't handle other cases such as K3 and G1 because these two functions have the same stack head. They are invoked in function C, which is called through function A and function B. To handle this mechanism, we can simply grab the function ID for the kernels using by reading the CU function argument passing through the CUDA launch kernel function. Therefore, currently we are going to use the stack head and the function ID as the identifier. However, then we encounter another problem to differentiate between the call stack associated with G1 and G2 because G1 and G2 have both the same stack head and the same function ID. Then to handle these kind of problems, we're going to provide you a concept of operation trees. So we see a GPU operation trees for a GPU API invocation is its prior operations launched before it. So for example, for G1, previously we have launched GPU operations K1, K2, and K3, which form a sequence. So this is the GPU operation trees for G1. Similarly, we're going to get the operation trees for G2, which is K1, K2, K3, and G1. Therefore, we can see that G1 and G2's operation trees are different, even with a tree size of 1, which looks back one's operation before the current operation. We don't want to keep a very large tree size because that's going to increase the comparison cost and also the storage for all the trees associated with each GPU API. However, even with this seem to be complete mechanism, we still have problems in some extreme cases. For example, here, we cannot use this identifier to differentiate between G2 and G3 because they have the same stack head, function ID, and operation trees. To handle these kind of complicated situations, we provide a Backoff mechanism. Basically, in this mechanism, we will unwind randomly at GPU APIs to get an accurate call path P. Then we will compare P to the call path P prime that the current identifier maps to. If P equals P prime, then we're going to reduce the unwinding probability of the current identifier, which means that this identifier can accurately identify the call path. Otherwise, we'll keep the high unwinding probability for the current identifier. So for extreme cases where we cannot use the identifier to identify the call path at all, then the unwinding probability will be its initial unwinding probability throughout the execution time. So we have measured our tool's overhead by studying various applications on a platform equipped with the AMD CPU and NVIDIA A100 GPU. We can see that our tool's overhead in average is only 1.4x comparing to HPC toolkits overhead of 2.1x and Insight Systems overhead of 2.7x. Besides, after inspecting the detailed overhead, we have seen that our tool's unwinding overhead is only 1.25%, which means that other overhead ranges from 39 to 35% comes from the CUPT monitoring tool, but not our tool. So we have also compared our tool's accuracy by calculating the number of correct call paths over the total number of call paths. Then under each setting of the initial unwinding probabilities, our tool's unwinding accuracy using the unwinding identifier is greater than 99.8%, which means most of the time we can use the identifier to identify the call path uniquely. Then in the next part, we are going to go through profiling of fine-grained metrics with low overhead. We call our profiling mechanism Epoch Profiling. So before getting started with collecting in fine-grained samples, I'd like to give you a little bit of background about instruction sampling on GPUs, since we are going to focus on collecting fine-grained instruction samples. Our method can also be applied to instrumentation-based metrics. So on a GPU, instruction sampling is performed on each streaming multiprocessor individually. Then after the execution of a kernel is done, then the monitoring runtime will collect all the samples, instruction samples from all the streaming multiprocessors and aggregate them into a table, which has each sample's PC, store reason, and number of samples. Then we can use this table to summarize the main store reason for each GPU kernel. However, it is noteworthy that by default, instruction samples are not correlated with GPU kernels. So with this limitation, the simple method to get instruction samples correlate with GPU kernels is by serialized profiling, which means that we're going to stop GPU kernel and copy instruction samples from the GPU to the CPU for every kernel. For example, in the timeline, we're going to first launch a GPU kernel A. Next, after this GPU kernel is done, we can synchronize the CPU and the GPU and copy instruction samples to the CPU for attribution. The same process is repeated for GPU kernel B. Obviously, the synchronization, copy, and attribution process can cause high overhead. To give you a more specific example, using this approach, HPC toolkit can cost about 27% in average, and on-site compute can cost 14,400x overhead. So another way to collect instruction samples with less overhead is using continuous profiling. Previously, we're going to stop the execution on the GPU and copy all the samples from the GPU to the CPU for every kernel. However, in the continuous profiling mode, we're only going to synchronize the CPU and the GPU at some point after many GPU kernel executions. Then, at that point, we're going to copy instruction samples from the GPU to the CPU. Since each GPU function has its range of PCs, starting from a PC and ending in another PC, we can match instruction sample PC with each GPU kernel. However, this method doesn't apply if two kernels are launched from different call paths, since in that case, two call paths will have exactly the same GPU kernels, but since we don't know how to attribute GPU samples of these kernels to each of the call sites. So here we formally propose our profiling method called Epoch Profiling, which groups GPU kernels into epochs. We're only going to apply a synchronization and copy at the end of each epoch, which is going to balance the profiling overhead and accuracy. The most naive epoch profiling variant is called fixed epoch profiling, where we divide epochs into equal number of GPU kernels and perform synchronization and copy at the end of each epoch. But in this case, if an epoch is quite large, then it could still have different call paths invoking the same GPU kernel. To improve this method, we devised another variant called adaptive epoch profiling. In this method, we will maintain a call path map M to map kernels to where they are launched. And we'll start a new epoch if the next GPU kernel has a different call path than in the call path map M that we are maintaining. Next, I will go through a simple example to illustrate this adaptive epoch profiling method. Suppose we have both CPU and GPU timeline. At first, we launch a GPU kernel K1, which means kernel K at the first call path. Next, we'll keep launching GPU kernels without stopping. Next, after launching serious kernels, here we invoke GPU kernel D1, which invokes kernel D at the first call path. But after that, we are going to invoke another kernel D2, which means we invoke D at the second call path. Since D2 and D1 invoke the same GPU kernel at different call paths, we see D2 conflicts with D1. So we need to, based on our rules, we need to synchronize the CPU and GPU and copy out the samples for attribution. Next, we're going to start a new epoch starting from D2. Therefore, in this method, we can accurately divide GPU kernels into different epochs, where in each epoch, we don't have the same GPU kernel launched at different call paths. To further reduce the measurement overhead and the storage overhead, we first proposed Epoch Sampling. We observed that repeated kernel launches subsequences often share the same behavior. Therefore, we randomly enable profiling of the same sequence with the enabling rate E. Given the following sequence as an example, at the start, we are going to profile kernel A0, kernel B1 through kernel C2. Then since A1 conflicts with A0, we're going to stop here and call the sequence before as an epoch. Then we start another epoch. Next, after a series of kernels, we encounter A0 and B1. Since A0, B1, this subsequence has been seen before, we can skip profiling for this subsequence and only restart profiling when we encounter C3, which we haven't seen before. Beyond that, we also proposed Epoch Aggregation to aggregate epoch metrics from epochs with the same kernel launch sequences. In this example, since A0, B1 appears 2 times, we can aggregate their metrics together to epoch E0. And for A1 and C3, since they only appear 1 time, we cannot aggregate their metrics. Here, subsequence matching is implemented by a try with GPU kernels. So after providing the methodology of our tool, next I'm going to illustrate how profile trees are implemented by our tool. At runtime, we keep 2 profile trees, including the epoch profile tree and the application profile tree. In the epoch profile tree, we're going to keep GPU samples under each epoch we created at runtime. For example, in epoch 0, we encountered function A and function B. Both have a set of instruction samples under it as children. And for epoch 1, we only encounter function B. Then post-mortem, we're going to iterate through all the epochs and assign samples to the CPU calling context tree created at runtime. At each epoch, since we guarantee that each function only appears at a specific call site, we can guarantee that the attribution is accurate. So in epoch E0, we can accurately attribute samples of function A to call site A1 and attribute samples for function B to call site B1. Similarly, we attribute samples of B in epoch 1 to B1. However, this mechanism doesn't resolve a complicated case where we have device function invocation. Suppose we, in epoch E0, we have a function C called by both function A and function B, then we cannot simply attribute samples associated with C to either functions. So in this case, we derive a rule to post-mortem apportion samples according to call counts to C in function A and B. First, we are going to analyze the number of samples and its call count of device function C. We found that there are 6 samples in device function C, and A calls C 1 time, B calls C 2 times in epoch E0. In this case, we are going to apportion samples and assign 2 samples to function A and assign 4 samples to function B based on their call counts. We have measured our fine-grained profiling mode with high and low enabling rate. High enabling rate means we frequently turn on instruction sampling. Low enabling rate means that we will skip instruction sampling for many times when we see repeated sequence. We have compared our tool's overhead with HPC toolkit. We found that our tool's average overhead is only 2.8x, which is a 10x reduction comparing to HPC toolkit. Even with high enablement rate, our tool's overhead is much lower than HPC toolkit. We measure our tool's fine-grained instruction profiling accuracy by calculating the difference of instruction samples between Epoch profiling and the serialized profiling. We assume the serialized profiling always render the correct result. We can see that with the low enablement rate, sometimes our tool's accuracy can go below 85%, but with high enablement rate, our tool's accuracy is always above 90%, and it is in average 96% among all the benchmarks we have tested. In the end, we have evaluated our tool's individual techniques to reduce CPU memory consumption at runtime. We can see that we started with basic Epoch profiling that has 8.8 gigabytes memory usage in average, but then with sampling and aggregation, we trimmed the memory consumption down to 3.1 gigabytes, which is comparable to HPC toolkit's 2.8 gigabytes memory consumption. To summarize, our tool provides CPU and GPU calling context information for GPU accelerated applications with low overhead. There are two techniques I'd like to highlight in the end. First, we use memoization based on unwinding for coarse-grained metrics, which results in a 1.5x overhead reduction comparing to the state-of-the-art tool with 99% accuracy. In addition, our Epoch profiling method can collect fine-grained metrics with 5.1x overhead reduction comparing to existing tool and yielding 96% accuracy. Our tool can be downloaded from the GitHub, and our code is available at HPC Toolkit's new Capti rebase branch. Please feel free to email us if you have any question. Thanks for attending the talk.